Hi group. This video lesson is going to be focusing on acids and bases. The learning goals for the video are listed here. So some key terms that we need to look at in item number 3. There's the definition of acids and bases according to a theory called the Arrhenius theory. We're looking at writing chemical equations for representing the solution formation for acids and bases and distinguishing between strong and weak acids and bases by their chemical properties. When we look at a list of compounds, here's a good variety of compounds. Some are ionic, some are molecular. We find that within that, anything labeled I in the second column is ionic, and we see a range. Some are soluble, some are aqueous. We have, for molecular compounds, some are not acids and some are. So clearly, the chemical behavior of compounds is not easily predicted just from the chemical formula. When we look at experimental evidence, here are a couple tables you'll find in your textbook on pages 362 to 363. It's a bit of a summary of things that chemists have observed over history, and it wraps up that previous list of compounds to say that most molecular compounds are non-acidic or basic. They have no effect on litmus. Most of them are not aqueous. They're not easily dissolved. If we have ionic compounds as our focus, most of them do dissolve easily. Most of them are non-acids or bases, but that's again why it was qualify with most, because there are exceptions here. For acids and bases, they are easily soluble, and they definitely have an effect on litmus. The different conductivities can vary from not at all in the solid phase for all of them, to some of them being conductive in the liquid phase, and most of them being conductive in the aqueous phase. When we look at compounds that contain hydrogen, you may have noticed from that chart that when the chemical formula starts with a hydrogen, then it's typically an acid. So if we have aqueous hydrogen nitrate right here, we have aqueous hydrogen sulfate, and it's easy to spot these. Okay, aqueous hydrogen sulfite. Containing a hydrogen alone, though, is not a guarantee of a compound being an acid. So over the history of acids and bases, generalizations were obtained, and here, looking at table 2, we see that hydrogen containing compounds vary from either being acids in that they change litmus paper red, or in some cases they have no change, indicating that they're non-acidic. So something about whether or not the compound actually releases hydrogen ions in an ionization process that's really important. And so clearly the litmus chemical in litmus paper responds to the presence of the hydrogen ion, turning it red. These two chemical reactions shown beside the arrow are ionization processes. So starting either with a molecular gas or an aqueous compound, molecular in form, we produce hydrogen ions for compounds that are acidic. And so that is one of the keystones of the Arrhenius theory for acids, is that compounds that contain hydrogen release them as hydrogen ions, and the hydrogen ions can react with hydroxide ions to produce water for neutralization processes. Bases, on the other hand, we'll look at are more related to what happens to the compound when they dissolve, in that they'll produce hydroxide ions. We have conductivity and litmus tests. So to fill this in, for molecular acids and ionic bases in solid form, we saw those in the chart. They were non-conductive. So we're just summarizing experimental results here. Unlike molecular acids, some ionic bases, because they're made up of ions, when you melt them, the ions are free to move around and they can be conductive. And then we have, when bases or acids are dissolved in water, we have aqueous solutions. They tend to be conductive. Now, acids and bases, when they're dissolved in water, must release ions in order for them to be conductive. And in this case, the effect on litmus has been seen before. Red is the color that litmus turns in the presence of an acid, and blue in the presence of base. A neutral compound is sort of an exception, would have no effect on either. So that's important to realize, that neutral compounds won't change red or blue litmus paper. So the Arrhenius theory was that based on knowledge of the compound's chemical formula, starting with maybe the acids, we've looked at that from those tables, that molecular acids must ionize, they must produce ions in order to have conductance. And the general way we can write this is that a compound containing some anion and a hydrogen ion, when water is added, they ionize to produce aqueous hydrogen ions, and this capital A is some anion. Could be the nitrate ion, the sulfate ion, depending. Maybe chloride. So for example, liquid phosphoric acid would release 3 hydrogen ions for every molecule in the presence of water. So when we add water to this, that enables it to ionize. The water molecules have an effect on separating out hydrogen ions from the compound. Reading from the textbook here on page 363, Arrhenius assumed that the water somehow causes the acid molecules to ionize, but he didn't propose an explanation for this. And in brackets it states, "We now believe that water molecules help to pull the molecules apart to ionize the acid." So often in science we don't have necessarily an explanation for why something happens, but we just observe the result in that they're conductive and they have an effect on litmus paper. So the other anion, which of course here would be the phosphate, balances the charge as follows. Okay, now going back to bases, most bases that we're familiar with are ionic hydroxides. So ionic hydroxides dissociate. We've looked at this process before. Now dissociation is just a separation of ions that are already present. Ionization, on the other hand, is a creation of ions that were not previously present. So to make that distinction, you might want to put a little asterisk beside ionize. Ions are created when a molecular acid ionizes, whereas in the case of a base, ions just simply separate. Okay? Now, generally we can call the metal cation, or typically it would be metal cation, might be a polyatomic in the case of maybe ammonium hydroxide, but the positively charged ion would be represented as M+. In the presence of water, we get that ion as well as the hydroxide ion, which is the ion that has an effect on litmus paper, and of course producing ions in solution always leads to conductivity. So for example, barium hydroxide, barium is a group 2 metal cation and has a charge of 2+, so that would be our valence on the metal cation here, and we would produce 2 hydroxide ions for every unit that dissociates. Of course, we have to remember that because these are solids, we still need to get them to dissolve, and water of course is going to act on those to separate them because of its polarity, but the extent of dissociation depends on the solubility of the base. So we have to remember that solubility, which has been defined previously in chapter 7, which was the amount of solute per volume of solvent, is going to be relevant here. Some ionic hydroxides aren't actually very soluble. Magnesium, calcium, barium, some of those group 2 compounds actually don't dissolve that well. So solubility is an important factor here. We can't assume that the dissociation happens 100%. Now, speaking of the amount of ions that we get, we could sort of quantify this with the percent ionization or percent dissociation. More commonly for acids, we look at percent ionization. And this is important when we're looking at how strong is the acid. The strength of an acid relates to the amount of hydrogen ions which are released from the molecules when water is present. Percentage ionization would quantify this, and it allows us to kind of separate acids into either strong or weak. Let's have a look at just a couple of little animations to illustrate for a strong or weak acid what's occurring in solution.
Hydrochloric acid is a strong acid. The compound hydrogen chloride ionizes completely, so many ions are free in the solution. Hydrofluoric acid is a weak acid because it only partially ionizes. At any one moment, most of the HF molecules have not split into their ions.
Hydrochloric acid is a strong acid. Strong acids are strong electrolytes, which for most purposes are assumed to ionize completely in water. In this case, HCl ionizes completely to hydrogen ions. Hydrofluoric acid is a weak acid. Weak acids are weak electrolytes, which only ionize to a limited extent in water. At equilibrium, a hydrofluoric acid solution contains mostly non-ionized acid molecules, HF, and a small amount of hydrogen ions, H+, and the conjugate base ions, F-.
Okay, so as you saw in those animations, that is our theoretical understanding of what occurs in a solution. It's based on empirical measurements, so we can measure the conductivity of a solution, and then what you're really measuring there with the conductivity meter is the number of ions. So in this case, the meter on the left is measuring the conductivity of a solution of acetic acid, and on the right, hydrochloric acid. It's stated here that the solutions have equal concentration, which means that for our chemical formula we have HCl molecules, and in acetic acid we have hydrogen acetate. And so here the number of molecules that are present at the beginning is equal. That's important. Question is how much they ionize. So if we have few hydrogen ions present in the solution, it would indicate a low percentage ionization, and many ions of hydrogen in solution would indicate high percentage ionization and high conductivity, and they go together. So you'll see in this chart here the electrical conductivity for different acids. The classification of weak is always associated with low conductivity, and strong is associated with high conductivity. The acid formula here, we see for acetic acid, nitrous acid, carbonic acid are all sort of categorized as weak acids, and then hydrochloric, sulfuric, and nitric are classified as strong acids. The distinction between weak and strong is a little bit more precise. So quantitatively strong acids, we assume that more than 99% of all molecules ionize, and for a weak acid, less than 50. You may have heard the term equilibrium in the video, and the term equilibrium refers to a balanced state where the rate of the forward reaction and the reverse reaction are equal, meaning that molecules HA can be breaking up into ions H+ and A- at the same rate as those ions are reforming back into molecules. But in a strong acid, mostly all of the molecules ionize into hydrogen and A-. In a weak acid, fewer than 50%. So we could say in the strong acid that the equilibrium lies far to the right in the product side, and for a weak acid, depending on how weak it is, the equilibrium favors more the molecular form, which is why a weak acid doesn't have very high conductivity, nor does it have very low pH. For strong bases, those that are easily dissolved and have high solubility, we assume dissociate almost 100%. High conductivity and low conductivity for strong and weak acids respectively, and the percentage ionization is greater than 99% or less than 50% ionized. Some examples are shown there. Finally, for neutralization process, acids and bases react together in that neutralization reaction. We can define them by formula as HA and MOH according to the definitions previously given, either releasing hydrogen ions or hydroxide ions. Remember that A is an anion and M is a cation. So because they have opposite charge, when these two types of chemicals react together, we get a new compound which we could call a salt, which would be Ma, aqueous, and we would get water, H2O. If we start with aqueous acid and aqueous base. Coming back to our learning goals here. So these key terms, ionization and dissociation, were used. You'll know now that ionization refers to acids, dissociation to bases. Strong and weak refers to only acids. Dilute and concentrated could refer to acids or bases. This is the key difference between them. So when we say that an acid is strong or weak, we're talking about percentage ionization. When we talk about a solution as being dilute or concentrated, it could be an ionic compound or it could be an acid or a base, but regardless, we're talking about the amount of solute. Regardless of what's happening, whether it's ionization to a high extent or a low extent, whether it's highly dissociated or just slightly dissociated, the dilution or the concentration of the solution has to do with how much solute we have present. Okay, so that's the key difference between those. So when you're using those key terms in your writing, just make sure you use them appropriately. At this point, you've seen, I think, all examples here for these learning goals, and now we can go through in class tomorrow, having completed that note, looking at some practice questions and some independent work on your own. Take care.